A Series RLC circuit is simply a resistor R, an inductor L and a capacitor C connected one after another in a single loop. When we apply an alternating voltage, each element stores and releases energy in a different way. The resistor turns electrical energy into heat, the inductor stores energy in a magnetic field, and the capacitor stores energy in an electric field. Resonance occurs when the energy that is temporarily stored in the inductor exactly cancels the energy stored in the capacitor at a particular frequency. In that condition, the two reactive parts' inductive reactance X sub L equals omega L and capacitive reactance X sub C equals 1 over omega C become equal in magnitude but opposite in sign, so they balance each other out. The fundamental resonant condition is therefore X sub L equals X sub C, omega L equals 1 over omega C, omega squared equals 1 over LC. This single frequency, called the resonant frequency, is the point where the circuit behaves like a pure resistor. All the wiggle from the inductor and capacitor disappears from the overall impedance. An everyday analogy is a playground swing. The swing representing the inductor wants to keep moving forward, while the child's legs pulling back, representing the capacitor, want to stop it. At a special timing, the resonant frequency, the pushes and pulls cancel perfectly, so the swing moves smoothly without extra effort, just like the Series RLC lets current flow without extra opposition. Explanation: starting from the resonant condition X sub L equals X sub C, we write omega L equals 1 over omega C. Multiplying both sides by omega gives omega squared LC equals 1. Solving for omega yields the resonant angular frequency. Omega naught equals 1 over square root of LC. To convert to ordinary frequency, F in hertz, we divide by 2 pi. F naught equals omega naught divided by 2 pi equals 1 over 2 pi times square root of LC. Numerical example. Suppose L equals 10 millihenry, 0.010 henry, and C equals 100 nanofarad, 100 times 10 to the minus 9 farad. LC equals 0.010 times 100 times 10 to the minus 9, equals 1.0 times 10 to the minus 9. Square root of LC equals square root of 1.0 times 10 to the minus 9, equals 3.1623 times 10 to the minus 5. Omega naught equals 1 over 3.1623 times 10 to the minus 5, approximately 31,622 radians per second. Convert to hertz as F naught equals 31,622 divided by 2 pi, approximately 5,032 hertz. So a 10 millihenry inductor with a 100 nanofarad capacitor will resonate at about 5 kilohertz, a frequency you could hear as a low-pitched tone if driven by an audio amplifier. At resonance, the inductive and capacitive reactances are equal and opposite, so they cancel. X sub L minus X sub C equals 0. The total impedance of a series RLC is Z equals R plus J X sub L minus X sub C. Because the imaginary part disappears, the impedance collapses to a purely real value. Z sub raise equals R. A purely real impedance means the voltage and current are in phase. The phase angle theta, defined by theta equals tan inverse of X sub L minus X sub C over R, becomes theta equals tan inverse of 0 equals 0 degrees. In other words, the circuit looks just like a resistor at the resonant frequency. Analogy: think of a tug of war where two teams pull with exactly the same force in opposite directions. The rope stays still, and only the middle person, the resistor, feels a net push. Similarly, the RLC sees no net reactive push, leaving only the resistance. Explanation: the quality factor Q tells us how sharp the resonance is. A higher Q means a narrow, tall resonance peak, while a low Q spreads the peak out. For a series RLC, the standard definition is Q equals reactive energy stored divided by energy dissipated per radian equals omega naught L over R equals 1 over omega naught RC. Both forms are equivalent because omega naught equals 1 over square root of LC. Calculation example using the previous numbers: L equals 10 millihenries, C equals 100 nanofarads, and choosing R equals 5 ohms. Omega naught equals 31,622 radians per second. Q equals omega naught times L divided by R equals 31,622 times 0.010 divided by 5 equals 316.22 divided by 5 approximately 63.2. Alternatively, using the second form, Q equals 1 over omega naught times R times C equals 1 over 31,622 times 5 times 100 times 10 to the minus 9, approximately 63.2. A Q of about 63 means the resonance is fairly sharp. The bandwidth will be about 1 over 63 of the resonant frequency. Intuitive picture. Imagine a swinging pendulum that loses a little bit of energy each swing because of air resistance the resistor. If the resistance is small, the pendulum swings many times before stopping, high Q. If the resistance is large, the swing dies quickly, low Q. The bandwidth delta omega is the range of angular frequencies over which the circuit's power falls to half its maximum, the -3 decibel points. For a series RLC, the famous relationship is delta omega equals omega naught divided by Q. Since we already computed Q in the previous example, approximately 63.2, and omega naught equals 31,622 radians per second, the bandwidth is delta omega equals 31,622 divided by 63.2, approximately 500 radians per second. Convert to ordinary frequency. Delta F equals delta omega divided by 2 pi, approximately 500, divided by 2 pi, approximately 79.6 Hz. Thus, the circuit will effectively pass frequencies from roughly 5,032 Hz plus or minus 40 Hz, approximately 4.99 kHz, to 5.07 kHz. Real-world analogy: think of a radio tuner that can select a station. A high Q tuner selects a very narrow station, little adjacent channel interference. A low Q tuner lets a broader chunk of the spectrum through, which may cause overlap. At resonance, the current through each element is the same because they are in series. Let the RMS current be I. Then, voltage across the resistor, V sub R equals I times R, purely real. Voltage across the inductor, V sub L equals I times X sub L equals I times omega naught L, leads current by 90 degrees. Voltage across the capacitor, V sub C equals I times X sub C equals I times 1 over omega naught C, lags current by 90 degrees. Because X sub L equals X sub C at resonance, absolute V sub L equals absolute V sub C. The two reactive voltages are equal in magnitude but opposite in phase, so they cancel when added vectorially, leaving only V sub R as the total applied voltage. Sample calculation. Use the previous circuit. R equals 5 ohms, L equals 10 millihenry, C equals 100 nanofarad, omega naught equals 31,622 radians per second. Assume the source supplies 10 volts RMS at resonance. I equals V source divided by R equals 10, divided by 5 equals 2 amperes RMS. Resistor voltage, V sub R equals I times R equals 2 times 5 equals 10 volts, as expected. Inductive reactance, X sub L equals omega naught L equals 31,622 times 0.010 equals 316.2 ohms. Capacitive reactance, X sub C equals 1 over omega naught C equals 1 divided by 31,622 times 100 times 10 to the minus 9 equals 316.2 ohms. Inductor voltage magnitude, V sub L equals I times X sub L equals 2 times 316.2, approximates 632 volts leading. Capacitor voltage magnitude, V sub C equals I times X sub C equals 2 times 316.2, approximates 632 volts, lagging. If you draw these as vectors, V sub L points 90 degrees ahead of the current, V sub C points 90 degrees behind, so they cancel and you are left with the modest 10 volts across the resistor. This huge voltage magnification inside the circuit is why series resonance is used in voltage step-up circuits such as RF transmitters. Analogy: picture two people pulling a rope with equal strength in opposite directions, while a third person in the middle holds the rope steady. The middle person feels the full pull, the resistor, while the two outer people feel large forces that cancel each other out. Power in AC circuits has three parts. Real active power P, the average power actually converted to heat, light, etc., measured in watts. Reactive power Q, power that oscillates back and forth between the source and the reactive elements L and C, measured in VARs. Apparent power S, the vector sum of P and Q, measured in VA. At resonance, the reactive parts cancel, so the circuit draws only real power. Mathematically, for a sinusoidal source of RMS voltage V and RMS current I with phase angle theta, P equals V times I times cosine theta. Q equals V times I times sine theta. S equals V times I. Since at resonance theta equals 0 degrees, we have cosine theta equals 1, sine theta equals 0. Thus, P sub raise equals V times I, all apparent power becomes real. Q sub raise equals 0, no reactive power. Power factor PF equals cosine theta equals 1, unity power factor. Using the earlier example, V equals 10 volts RMS, I equals 2 amps RMS. P equals 10 times 2 equals 20 watts. No reactive power flows, even though the inductor and capacitor each have a 632 volts RMS voltage across them. This is why resonant circuits can handle large voltages without drawing extra power from the source. The energy simply sloshes back and forth between L and C. Real-world analogy: think of a child on a swing, reactive energy, who gets pushed periodically. The child's kinetic energy, real power, comes only from the pushes that are in sync with the swing's motion. At resonance, the pushes are perfectly timed, so all the effort from the pusher becomes useful motion. There is no wasted back and forth effort. When we first connect a DC source to an unenergized series RLC circuit, the current does not instantly reach its steady-state sinusoidal value. Instead, the circuit exhibits a transient natural response that is a damped sinusoid. LD squared I over dt squared plus RDI over dt plus I over C equals dV sub S of t over dt. LD squared I over dt squared plus RDI over dt plus I over C equals 0. I of t equals e to the st. Ls squared plus rs plus 1 over c equals 0. S equals negative r plus or minus square root of r squared minus 4l over c, all divided by 2l. If r squared is less than 4l over c, the circuit is underdamped and the roots are complex conjugates. S equals negative alpha plus or minus j omega d. Alpha equals r over 2l, damping factor, and omega d equals square root of 1 over lc minus r over 2l squared, damped natural frequency. I of t equals I sub 0 e to the negative alpha t times sine of omega dt plus phi. Example: take L equals 10 millihenries, C equals 100 nanofarads, and a relatively small resistance R equals 1 ohm, so the circuit is lightly damped. Omega 0 equals 1 over square root of LC, equals 31,622 radians per second. Alpha equals R over 2L, equals 1 over 2 times 0.010, equals 50 per second. Since alpha is much less than omega 0, the damped frequency is omega d equals square root of omega 0 squared minus alpha squared, approximately square root of 31,622 squared minus 50 squared, approximately 31,621 radians per second. If the circuit is initially charged so that the capacitor voltage is 5 volts and the current is 0, the resulting current transient might be I of t equals 0.5 e to the negative 50 t times sine of 31,621 t amperes. The exponential term causes the oscillation to decay slowly. After about 5 time constants, 5 over alpha approximately 0.1 seconds, the oscillation is essentially gone, and the steady-state sinusoid driven by the source takes over. Physical picture: imagine a mass spring damper system. The mass inductor stores kinetic energy, the spring capacitor stores potential energy, and the dashpot resistor dissipates energy. With light damping, the mass bounces back and forth many times before coming to rest, exactly what we see in the underdamped RLC transient. 1. Find the resonant frequency. Write the formula F0 equals 1 over 2 pi times square root of LC. Plug in L and C, keep units in henries and farads. Compute the square root, then divide by 2 pi. If L times C equals 10 to the minus 6, then square root of LC equals 10 to the minus 3, and F0 equals 1 over 2 pi times 10 to the minus 3, approximately 159 kilohertz. 2. Calculate the quality factor Q. Use the most convenient form Q equals omega 0 times L divided by R, or Q equals 1 over omega 0 times R times C. You already have omega 0 from part 1. Insert L or C and R. If omega 0 equals 10 to the 5 radians per second, L equals 20 microhenries, R equals 2 ohms, then Q equals 10 to the 5 times 20 times 10 to the minus 6 divided by 2 equals 1. 3. Determine the bandwidth delta F. First, get angular bandwidth delta omega equals omega 0 divided by Q. Convert to ordinary frequency. Delta F equals delta omega divided by 2 pi. If Q equals 50 and F0 equals 1 megahertz, then delta F equals F0 divided by Q equals 20 kilohertz. 4. Find the voltage across L or C at resonance. Compute the circuit current at resonance, I equals V source divided by R. Compute reactance at resonance, XL equals omega 0 times L, same as XC. Voltage magnitude VL equals I times XL. Large voltage magnification occurs when XL much greater than R. For example, with R equals 5 ohms, I equals 2 amperes, and XL equals 300 ohms, VL equals 600 volts, while the source may only be 10 volts. VAS solve checklist. 1. Write down LCR and source voltage. 2. Compute omega 0 equals 1 over square root of LC, yields F0 equals omega 0 divided by 2 pi. 3. Find Q using omega 0 times L divided by R. 4. Bandwidth equals F0 divided by Q. 5. Current at resonance equals V source divided by R. 6. Reactive voltages equal current times omega 0 times L, or 1 over omega 0 times C. 7. Remember phase angle equals 0 degrees. Real power equals V source times I, power factor equals 1. Practicing these steps on a few numerical sets will build speed for exam situations.